Welcome to Compilers Interview Crashcasts, the podcast that helps you ace your back-end engineering interviews. I'm your host, Sheila, and today we're joined by Victor, a seasoned compiler engineer. We'll be discussing a common interview question. What is a compiler? Victor, are you ready to dive in?
Absolutely, Sheila. I'm excited to share my knowledge on this topic.
Great. So, Victor, let's start with the basics. Can you give us a simple definition of what a compiler is?
Certainly. In essence, a compiler is a program that translates source code written in a high-level programming language into a lower-level language, typically machine code or assembly, that a computer's processor can directly execute.
That's a great starting point. Can you elaborate on why compilers are important in software development?
Compilers play a crucial role in software development because they bridge the gap between human-readable code and machine-executable instructions. They allow developers to write code in languages that are easier for humans to understand and maintain, while still producing efficient programs that computers can run.
Interesting. Now, let's dive a bit deeper. Can you walk us through the main components of a typical compiler?
Certainly. A compiler typically consists of several key components. First, we have the lexical analyzer, also known as a scanner, which breaks down the source code into tokens. Then there's the syntax analyzer, or parser, which checks the structure of the code against the language grammar. Next, the semantic analyzer performs type checking and other semantic validations. After that, we have the intermediate code generator, which creates a midway representation of the code. Then comes the optimizer, which improves the intermediate code for better performance. Finally, the code generator produces the target code, usually machine code or assembly.
That's quite comprehensive. Could you explain the compilation process in more detail? How does the code flow through these components?
Of course, the compilation process is typically divided into phases. It starts with the lexical analyzer scanning the source code character by character, grouping them into meaningful tokens like keywords, identifiers, and operators. These tokens are then passed to the syntax analyzer, which checks if they form valid language constructs according to the grammar rules. Next, the semantic analyzer checks for things like type consistency, ensuring variables are declared before use, and so on. After that, the intermediate code generator creates a lower-level representation of the program, often in a form that's easier for the computer to work with. The optimizer then works on this intermediate representation, applying various techniques to improve performance and reduce code size. Finally, the code generator takes the optimized intermediate code and produces the target machine code or assembly language.
That's fascinating. You mentioned optimization techniques. Can you give us some examples of common optimizations that compilers perform?
Certainly. Some common optimization techniques include constant folding, where we evaluate constant expressions at compile time, dead code elimination, which removes code that doesn't affect the program's output, loop unrolling, where we replicate the body of a loop to reduce overhead, inline expansion, which replaces function calls with the actual function body, common sub-expression elimination, identifying and reusing the results of identical expressions, and register allocation, efficiently assigning variables to CPU registers.
Those are some interesting techniques. Now, let's consider some edge cases. How do compilers handle things like macro expansions or conditional compilation directives?
That's a great question, Sheila. Macro expansions and conditional compilation directives are typically handled by the preprocessor, which is often considered a separate phase that runs before the actual compilation begins. The preprocessor handles tasks like macro expansion, replacing macro invocations with their defined content, file inclusion, inserting the contents of header files, and conditional compilation, including or excluding code based on defined conditions. These operations can significantly alter the source code before it reaches the main compiler, which can sometimes lead to challenges in debugging or understanding the final compiled code.
You bring up an interesting point about debugging. How do modern compilers address the challenge of debugging optimized code?
Debugging optimized code is indeed challenging because optimizations can change the structure of the code significantly. Modern compilers use several techniques to help with this. They generate detailed mapping between source code and machine code, which we call debug information. They also offer different levels of optimization, allowing developers to balance between performance and debuggability. Some systems use just-in-time compilation, or JIT, which can provide more accurate runtime information. Additionally, some compilers can de-optimize code on the fly to provide more accurate debugging information when needed.
That's really helpful, Victor. As we wrap up, could you share some real-world applications where compiler technology is particularly important?
Absolutely. Compiler technology is crucial in many areas. In high-performance computing, it's essential for squeezing out every bit of performance. In embedded systems, where resources are limited, compiler efficiency is paramount. Compiler design also heavily influences the development of new programming languages. In web browsers, just-in-time compilation is used to speed up JavaScript execution. And in mobile app development, ahead-of-time compilation is often used to improve startup times.
Thank you, Victor. That was an excellent overview of compilers. Now, for our listeners preparing for interviews, here are some key takeaways. Start with a clear, concise definition of a compiler. Be prepared to discuss the main components and phases of compilation. Understand common optimization techniques. Consider edge cases like pre-processing and debugging optimized code. And think about real-world applications of compiler technology. Remember, interviewers are often looking for depth of understanding, so don't be afraid to dive into details. At the same time, be sure to communicate clearly and structure your answers logically. That's all for today's episode of Compilers Interview Crashcasts. Thanks for listening, and good luck with your interviews.